All right, good morning, everyone. Let's begin chapter 1 today. I haven't had, well, some students emailed me about minor issues that they had with the system, but overall, I'm assuming that students were able to log on to Pearson's Mastering Engineering, also Microsoft's OneNote, the class notebook, because I haven't received any emails about those. So I would assume if you had any issues, you would get in touch with me. So at this point, I assume that there were no other issues. All right. Okay. I'm also happy to report IT did install the drivers and I was able to get everything working last night. So technology is again wonderful until it stops working or it doesn't work. New share. So this is the class notebook where I would teach by writing annotations and class annotations. And if you've signed up for the class notebook, it'll automatically appear at your end. Okay. So as an example, my chicken scratch, if it's not readable, just let me know, right? I'll wipe it and write it again. Familiar with this sentence? Yeah. I keep practicing, but my handwriting doesn't improve. All right. So it should, if you are logged on to the class notebook, it should appear at your end. Anyway, everybody's familiar with Tesla, the car company, and also most likely Nikola Tesla. Tesla was I believe he was born in a town in what is now known Serbia, somewhere in Serbia, I think. European engineer. He was a brilliant physicist. He had some accounts say that he had an eidetic memory. I don't know if that's true or not, which is what, people say that's photographic memory. But eidetic memory means he could like remember stuff just by reading about it once or knowing about it once. Let's see. I just want to make sure. Yeah, okay, right. And then recording is on. Okay. All right. Anyway, so he was a brilliant physicist. He was working in Europe at the time, late 1800s, and he was working with electrical motors, induction motors specifically. And Edison at the time was already an established inventor. He had his, well, for lack of a better word, I would say like a factory farm where he had hundreds of engineers employed, and they were all working, towards one of his projects, right? And so at that time, one of the managers that was working with Edison knew about Tesla, and so he was in Europe for like a meeting or a conference, or maybe he just went to recruit him. No idea. But that manager convinced Tesla to come over to America and then work with Edison. Okay, so at the time, the story goes that there was a unsolvable problem. There was a problem that had stumped Edison and a lot of other people at his company, and he had a sort of a bounty about a few $1,000s, which would be about close to millions of dollars today. And no one was able to solve it. The story goes that Tesla came. He worked for Edison for a while. He was able to solve it. And when he asked for his, asked for the prize, Edison laughed in his face and he says, I was just joking about it. You are my employee. It was just part of your work. I don't know if that's true or not, but apparently there were some disagreements between the two. And then Tesla left Edison's employ shortly thereafter. From that point on, Edison went all out and did everything in his power to denigrate Tesla and all and his work. Okay. He was a very vindictive person. Anyone see the Big Bang Theory? There's an episode where they talk about the war between Edison and Tesla. That war came to be known as the War of the Current, but there was a lot of other, things that were behind it. So one of the stories, as I said, was they were working together, and they had a fallout, disagreements over lots of things. From all accounts, Edison was someone who was more kind of hands-on, and he would, instead of actually doing the theoretical work, he would simply avoid it and just try to actually, get a practical thing working. So some accounts also say is he didn't do that work because he was unable to do it. And again, there's no shame in that, but if he wanted to be like a big personality, he had the charm, he had the charisma to obtain lots of money from other people, trying to get them invest in this country, invest in his company. And so what he wanted to show was, hey, I can do this thing. So he would just go and start building stuff. If it didn't work, he would try it again. It didn't work, he would try it again. And so again, they say when he invented the light bulb, there was lots of other light bulbs, theory around, and he made so many of them before he got a working one. Tesla was the opposite. He was a mathematical genius. He could do complex math, arithmetic math in his head, and he would work out all the problems and issues theoretically on paper before he would actually get to the actual physical device. So at the time, this was the late 1800s, where there was a lot of focus on generating and delivering electrical power, right? Imagine if you didn't have power, you wouldn't be doing any of this. So electrical power at that time, there were two competing technologies, DC and AC. DC stands for direct current, AC stands for alternating current. We'll talk about that in just a little bit in the next slide. But the story is that Edison had his own company that was backing DC, one technology competing against another. Okay. At the time in 1886 or 1889, I believe, somewhere around that time period, the World's Fair was taking place in Chicago. And both of these companies, Tesla, by the way, had the backing of George Westinghouse. Westinghouse is a brand that is still in existence today. They still make some sort of consumer electronic devices and they sell them. Anyway, so Edison had his company, Tesla had the backing of Westinghouse, and they both bid on lighting up and supplying electrical power to the World's Fair. Tesla's bid came in about $100,000 cheaper than Edison's company. And 100,000 in those days would be, I don't know, millions and millions and millions of dollars today, right? And so they got the bid. They were successful in implementing electrical power supply. People at the time were only familiar with like gas lamps and like very dangerous electrical wires. And so when they saw the successful implementation along with the safety, right? Imagine that all your life you're only seeing like oil lamps or gas lamps for lighting. And here comes along a technology that just invisible technology that is, just powering up and showing you light. It's very, very, I think it's frightening in some cases. As a segue, when trains were first invented and, they wanted people to, hop onto trains, there was a feeling that if you sat on a train or in a car, you would actually suffocate and die. Because people were only used to walking or running or being on horseback or in a horse-driven carriage. Now here comes along an automobile that can go at 25, 30, 40 miles an hour, which for us it seems very slow, but for those times it's pretty scary. And so people were actually afraid to go on an automobile or a train. Anyway, coming back to our main point. So electrical supply was considered to be dangerous at the time. When Tesla and Westinghouse successfully demonstrated a very safe installation of electrical power, well, AC kind of won from that point on. There's a lot more to that history and that story, of course, but that's kind of like the gist of it. There's also a movie that came out a few years ago. It's called The War of Current, I believe, or The Current War or something like that. It's an excellent movie. You should definitely check it out. It basically tells the story of how AC and DC technologies were introduced into the world. The world's first power station. Any guesses on where that was set up? Niagara Falls. It's still in existence today. I don't know if it's now a museum or it's still working, but that place is still in existence today. Okay. And when they first came up with it, again, as I said, people were afraid, right? People are getting electrocuted by just touching exposed wire and dying or having severe burns. And so they chose a limit of 100. Nice round number, which is not thousands of volts or hundreds of volts, but just enough to actually supply electrical power. They built in some tolerance to it, about 10%, and that's what we have in our power outlets today, at least in US and North America, right? So 110 volts, sometimes it fluctuates, it can go above or below, but that's the power outlets that we use in the US. In rest of the world, again, we'll see that when we get to the slide on power, but we use higher voltage, which is 220 volts, twice as much, okay? 220 volts allows you to supply a lot more electrical power, the same amount of current. If you have learned about Ohm's law in physics, you know the equation that I'm talking about, right? Anyone familiar with installation of hot tubs? Right, hot tubs. You might have heard that if you want to install a hot tub in your residence, you need an electrician to come out and do something. Have you ever heard of that? It's because hot tubs have a very big heater, require a lot of electrical power. And so there are two phases of electrical supply that come into your residences. There's actually one phase that comes in. I don't know if that's true anymore, but there's, different parts of the US have different requirements. So you have two phases of power coming in. One phase goes inside the house, the other one goes outside, something like that. So when you want to install a appliance or any device that requires a whole lot of electrical power, what they do is they take two phases and they put them together. So you have two phases going in. Now the voltage, instead of being 110 volts, is 220. And so your power is now increased without increasing the current. And so the licensed electrician would come out and would perform that installation work of wiring those two phases together to powering that hot tub. Okay, so 110 volts, as I was saying, power outlets. And this, of course, is also general knowledge. You don't need to be an engineer or an electrical engineer to know this. Power outlets supply 110 volts. You could take 122, but let's stick with 110. And it's not always constant. There's always some sort of fluctuation going on. So it might go lower, it might go higher, depending on the supply and the usage on that day. This is at least in the US and North America. In the rest of the world, or most parts of the world, it's 220 volts. All right, so DC and AC, the word current is baked right into it, okay? But do not get confused. Ignore the actual form of, the full form of DC and AC. We simply use the acronym DC and AC because this DC and AC acronyms can be used for voltage, can be used for current, can be used for power. All three physical quantities, we can use it for all three of them. So we say DC voltage, DC current, DC power. If we say DC current and you expand it, it simply becomes direct current. So don't get confused in the words, just simply understand the acronym. AC and DC stand for a fixed value versus a fluctuating value. Okay. So this is fixed. And this fluctuates. And so what do we mean by that? Well, a fixed value, or DC, simply means that the quantity has a value that does not change with respect to time. If you notice, x-axis is time. This is simply an illustration. It's a plot. It's a graph of the value of that quantity at any single point in time. A DC voltage or DC current simply notes that the value of that quantity does not change with respect to time. If you have a 5-volt battery, that battery will supply 5 volts irrespective of when you measure it. In real world, of course, if the chemicals inside that battery degrade, then that voltage level could go down. But theoretically speaking, 5-volt battery source will supply 5 volts. Its value will not change with respect to time. AC, on the other hand, the value does change with respect to time. Okay, any quantity, whether it's voltage, current, or power, any electrical quantity that changes its value with respect to time is classified as AC, which is pretty much every electrical signal. The talk, right? The sound signal that when I'm talking, there is sound that is being captured by the microphone. The microphone is a transducer that converts the sound signal into an electrical signal. That electrical signal will change its value depending on how I talk, whether it's high or low, it changes in value. So it's AC. Okay, it's AC. And AC has many forms. Whether it's voltage, current, or power, it could be a random signal like this that just fluctuates, right? So it's completely random. It could be a square-shaped waveform. It could be rectangular. It could be triangular. Or it could be sinusoidal. This is what we see here. And that signal, this signal, is the one that we will deal with for the most part in this class. Sinusoidal. Okay, and mathematically we will use trigonometry, sine and cosine, to actually represent this waveform. So this is sinusoidal, and the reason we call it as alternating is because the value alternates between a positive and a negative value. But again, in general, it doesn't matter how or where it alternates. It's just referred to as AC. Okay, any quantity that changes its value with respect to time is AC. All right, 10-second pause. Think over it. Let me know if you have any questions. Yes. Yes. So the question being asked is, if the value fluctuates, as you see in this figure right here, but stays positive all the time, so if the value stays positive or above 0 all the time, whether it's still AC or not, answer is yes, it will be AC. So that's why I said, do not get confused by the word alternating. So alternating would imply that it alternates between 2 points, right? Positive and negative. But again, ignore the actual word and just focus on the acronym. AC, anytime you see the word or read the word AC, it's simply changing its value with respect to time. All right, any other questions? And again, they can be, DC and AC is used for both voltage, current, and power. Okay, typical electrical circuit. Question is, what is circuit analysis? That is what you're here to learn, right? What is circuit analysis? So this is simply a schematic or an illustration of a typical electrical circuit. It has the 3 components that we will study in this class. And again, I assume you would have seen these symbols before in physics. Yes, I will still do a recap, of course. But what is circuit analysis? Circuit analysis is simply the techniques, the methods that we use to determine the value of the unknown quantities in that circuit. That's all circuit analysis is. Okay. Circuit analysis is simply the techniques and methods that you would use to determine and obtain the values of the electrical quantities in the circuit. So in this circuit, what we see is a voltage source right here. We have resistances or resistors, the component, and we have capacitance or capacitors, and inductance or inductors. Okay. Resistors are noted, excuse me, by the letter R. You hear me coughing, by the way, it's because I get dry throat from talking, and I also suffer from allergies. And resistance is a quantity, and as with most things that we have encountered in science and physics in our lives, a person who does a lot of the work gets credit for it. And so even though a lot of people did a lot of work in the resistances and inductances and capacitances, each one of them has been attributed to a single person. George Ohm was a physicist who did a lot of research in resistances and voltages and currents. And so the unit for resistance is named after him, Ohm. And it's typically noted with the Greek letter omega. Voltage, simply noted by the letter V. It's named after anyone? It's named after Volta. So volts or volt. No symbol for it. It's simply V. So again, that can get confusing. Voltage is noted by V, and the unit for voltage is volt, also noted by V. So sometimes we differentiate by using the lowercase v to indicate that we're talking about the quantity voltage, and the uppercase V for the unit volt. And then current is I, named after ampere or amp for short, or A. Power is P, named after James Watt. So Watt or W, uppercase W is lowercase w is used for anyone? Work, or in electrical engineering here, we use it for energy, work that is being done. Anyway, we'll get to that later. But for the most part, these are the quantities and the notations that we will use. All right. One point about conductors. Conductors are these lines that you see. Okay. These lines that you see are conductors. In real life, a conductor is basically a piece of wire that is used to make a connection between 2 points. So this USB cable is a conductor because it conducts electricity from one point to another point. The HDMI cable is also a conductor. It conducts or permits the flow of electricity. Okay. In real life, a conductor inherently has resistance, capacitance, and inductance. It just does not rise to the level of interference of its purpose. I could take an electrical power cable, extension cable, like the orange ones, and you could stretch it out for hundreds of miles. On paper, if you stretch it out for hundreds of miles, it still has 0 ohm resistance, It has zero inductance, it has zero capacitance. But in real life, it actually has resistance, it actually has inductance and capacitance. Okay. The point I'm trying to make is that on a circuit schematic, you could draw a conductor as a small dot or a small line or a really big line. They all have zero values. It doesn't matter. So I could take this circuit and I could draw it something like this. And it'd be very, very small resistor. Then I would have a capacitor. Oh. And then from this point on, I have another resistor and an inductor. It's the exact same circuit, just drawn a little bit differently. We take 10 seconds and see if it makes sense. Yes. Not until chapter 3. So conductor can be drawn on the schematic however you want. Typically, electrical circuits usually have the source on the left and the rest of the components on the right. But you could flip it around, it will still make the exact same circuit. So I could have the voltage source here. I could have the resistor here. I could have the capacitor like this. I could have the other resistor here and the inductor here. Again, it's the exact same circuit. So keep in mind, when you build this circuit in real life, it's going to look completely different. On your table in front of your eyes, it will look different. Schematic is just a way for us to understand how the circuit looks on paper or how it's going to behave. So this circuit on the left is exactly the same as the one down here, and it's exactly the same as the one down here. Right? So circuit schematic would change depending on what works for you. You can take the circuit and you can change it around however you want, but it still functions the same. Okay, any questions? One final note about this slide. Anything that provides energy is known as a source. Any component that receives the energy or consumes the energy is known as a load. So source supplies energy to a load. Anything that supplies energy is a source. Anything that consumes energy is a load. And so sometimes you would hear the words electrical load, right? Electrical load is just basically consuming energy. So resistors, capacitors, and inductors are all loads because they do not supply any sort of energy. Capacitors and inductors are energy storage devices. So if they have already received energy previously, they could supply energy. But it's not by itself, they are not a source. Speaking of sources and loads, if you see a circular symbol, it signifies it's a source or a measurement device. Measurement devices are also known as meters. Okay, if you have a circular notation, I know this doesn't look like a complete circle, but a circular notation indicates it's a source or it is a measurement device. If you put a plus and minus sign inside that circle, the plus and minus sign or symbol indicates its voltage. Voltage is nothing but the difference in electrical potential between any 2 points. Okay, voltage is nothing but the difference in electrical potential between any 2 points. We typically just use the words PD, potential difference. If there is no difference between the 2 points, the voltage is equal to 0. Okay, it does not necessarily have to be at a zero level or the ground level, which is what we typically reference to as zero. So coming back to this point, if it's a plus and a minus sign, it indicates voltage. If it's an arrow, it indicates current. It's current always flows through. Okay, current always flows through because you're talking about flow. Current is always through, and voltage is always across. And because it's the difference in potential between 2 points, it's always across 2 points. Okay, so voltage is always across, current is always through. And it could be drawn anyway. Again, it's a schematic. You can put it, going up, going down, going left, going right, doesn't really matter. So a voltage source could be something like this. It could be like this, be like this, or it could be like this. It doesn't actually make any difference. It's just a notation and a way of drawing the schematic. Same thing with the current. Current could go in this direction, could go this direction, could go this direction, or could go left. Measurement devices you would not see in especially in this class, you will not use this or come across anywhere. But it's just for your knowledge. A measurement device or a meter has the arrow at an angle. Okay, can everybody in the back see this? So this is I just noticed that it's projecting on the whiteboard. There is no screen. It might be a smart board. Don't know. Anyway, so as I was saying, an arrow at an angle simply is because when the first meters came out, they were analog dials. And hence, if the arrow is at an angle like that, it notes a measurement device or a meter. Yes. Yes. Yeah. So the question being asked is, if it's a current source and you have an arrow in there, which is either pointing straight up, straight down, straight left, or straight right, does it indicate the flow of the current? Absolutely. That's what it is showing. Yes. Yes. Yeah. So that was going to be my next point. So if it's a voltage source, current always goes from minus to plus. But we will get to that in about 2 or 3 slides. May or may not cover it today. Yes. Nowadays, no. When they first came out, analog meters decades ago, they were different. So the question being asked is, are the measurement devices different for voltage and current? And the answer is not anymore. Okay. So when they first came out, they were specifically for measuring voltage, specifically for measuring current, or specifically for measuring power. And so a voltage measurement device was known as a voltmeter. A current measuring device was known as an ammeter. Again, amp meter. And a power measuring device was known as a wattmeter or a power meter. And then someone came up with combination in one single meter, and so it came to be known as multimeter. And then came the digital ones, so they came to be known as digital multimeters or DMMs. And nowadays you can buy a handheld digital multimeter for about $5 or $10. It's just incredible how far we have come. So okay, gotcha. But it was still a nice segue. So the original question being asked was whether the same symbol with a slanting arrow is also used for voltmeters and ammeters. And the answer is yes, because you would note that it's a plus minus, it's measuring voltage or measuring current. Okay, any other questions? So, final point, what is the diamond? Does it note anything? The answer is yes. A diamond symbol notes that it is a dependent source. It's a dependent source. It is not independent. So we talked about how circle is for a source. When we say circle is for a source, the implied quantity in there is that it is independent. IN independent. It simply means that the source will supply its rated quantity value irrespective of what the load does. Okay, as long as it has the capacity. Now in real life, of course, all the sources are built with certain capacity. As long as the load requirements are within its capacity, it will supply it irrespective of what everything else is going on around it. And hence it is known as independent. A dependent source, which is noted by the diamond, and the symbol remains the same, plus minus for voltage, arrow for a current. A dependent source will supply that voltage or that current, but it depends on some other part of the circuit and is mostly used for theoretical calculations. And you will see this in 321 electronics. So again, a dependent source cannot supply a voltage or current without it being dependent on some other part of the circuit. One example of it might be, laptop adapters, right? Laptop adapters, you plug in, you charge it up. Most laptop adapters supply either 18 or 19 volts. Okay, 18 or 19 volts DC. What is the power rating for a USB port? Standard power rating. What voltage? 5 volts. Standard USB port, the specification states 5 volts. Okay, so the laptop is receiving 19 volts coming in. How is it supplying 5 volts? Well, there's a power circuitry inside the laptop which actually takes the 19 volts and steps it down depending on the requirement of the of the entire circuitry inside there. So the microchip, the main CPU inside the main processor inside the laptop motherboard requires about 3.3 volts or sometimes even less. Some other parts of the circuit might require like 5 volts. Some other parts of the circuit might require like 1 volt. Okay, so all of that is fixed. Now, let's say if it was not fixed, okay, you would have a combination of a resistor, 2 resistors, and you would supply 19 volts to those 2 resistors. If you have 2 resistors or more than 2, the voltage is going to break up into different parts. Okay, voltage is going to break up into different parts. So if the 19 volts changes to 10 volts, then a corresponding change would take place in a different part of the circuit. So that part of the circuit is now supplying, let's say previously if it was supplying 5 volts, and now it might supply like 2.5. Yes. No, it could be AC or DC, doesn't really matter. So again, as I said, it depends on a different part, excuse me, different part of the circuit for its value. Whether it's AC or DC does not matter. All right, any other questions? And again, we'll go a little bit further in this discussion as we go along. Wow, you're already at 10:50. All right, I don't have anything particular to talk about in this slide. I just like the meme. I used it for some high school talk for students who are not familiar with it. For the most part, we talked about the three Thors that we're going to look at. which is the resistor, the inductor, and the capacitor. Yeah, R, L, and C. Inductors are noted by L, capacitors by C. But again, we will look at those when we get to chapter 3. We will look at transformers a little bit. It's part of the syllabus, but just depending on how the quarter goes, we may or may not have time to go, deeper into it. And then transistor is an electronic device. It's a solid state electronic device. You will learn about transistors and diodes if you take EE 321. So a slight segue. EE 321 is the follow-on course, simply electronics. That's the name of the course, and it's a direct continuation of 201. So I know some departments do require their students to take 321, and for some it's a technical elective. If you do decide to take it, I am teaching 2 sections next quarter, and the format is exactly the same as this one, and the code is also exactly the same as this one. So if you do have to take 321, and if it fits in your schedule, you check out the 2 sections that I have next quarter. You will not need to purchase that code again. The same code will work for that class also. Okay, so just keep that in mind. All right. Let's say goodbye to Thor and go to unit prefixes. Now, as engineers, even in your own fields, you are used to working with very large quantities and very small quantities. So, there's this unit prefix system that has been developed, named after a lot of Greek letters, and you'll be familiar with some of them, probably with most of them. I don't expect students to memorize this. Even I don't have it memorized all the way down to like Zepto and Yocto. But for the most part, everybody should be familiar with the middle of the table. Okay, just to give you an idea, these are the 2 examples I like to use to give an example of very, very small size. Millimeter, a millimeter, again, very, very small, right? Everybody's used a scale or a ruler. Everybody knows how small a millimeter is. Millimeter is 10 raised to minus 3 meters. If you take 1 millimeter and you divide it into 1,000 parts, you get 1 micrometer, 10 raised to minus 6. Okay, 1 millimeter divided into 1,000 parts, 1 micrometer, 10 raised to minus 6 meters. To give you an idea of how small it is in real life, a human hair, which I don't have a lot left, is about 70 microns. Okay, 1 micrometer is also known as micron, like the company, Micron. So human hair is about 70 or 75 microns wide, and 1 micro is smaller than that. So hence, microchips, that's where it comes from. When they first came out, they were working on the order of 10 raised to minus 6 meters. Very, very small. And if you take 1 micron and divide it, incredible as it seems, even a further 1,000 parts, that is 1 nanometer. And the microchips that are built today are smaller than a nanometer. They're approaching the size of atoms. So 1 nanometer is 10 raised to minus 6, 10 raised to minus 9 meters. And we will see when we talk about inductances and capacitances, capacitance can be smaller, very, very small, like picofarads and femtofarads, 10 raised to minus 12, 10 raised to minus 15. So I would expect students to be familiar at least till this part of the table. Okay. On the other hand, when we're talking about large quantities, we are using terms like mega and giga and tera, even in general pop culture. You just look at the cordless phones that were used a few years ago, microwaves, wireless routers. They all have a frequency band of 2.4 gigahertz. 2.4 gigahertz is a band spectrum that FCC opened up for consumer usage several years ago. And so your cordless phones, when they first came out, nowadays, of course, everybody uses smartphones, but cordless phones in the house were connected to landlines. The frequency band they used was 2.4 gigahertz, which is right here, 10 raised to 9. Okay, microwaves, 2.4. Wireless routers were 2.4. Then it started getting very crowded, so FCC opened up 5 gigahertz. So now you have dual band routers that broadcast at a frequency of 2.4 and 5 gigahertz. It means it changes its value 10 raised to 9 times per second. Okay, 10 raised to 9 times per second. That's how fast it changes its value. Oh, by the way, power outlet. What is the power outlet rating in terms of frequency? 60 hertz. The value of the voltage and the current that comes out of the power outlet, it goes up, goes down, goes up, goes down, goes up, goes down 60 times in 1 second. If you were Dr. Strange and had the power to slow down time, you could stick your finger in the wall and you could feel it going up and going down. Just don't stick your finger in the wall. But that's what 60 hertz means. 60 hertz is a very, very low frequency compared to what we actually use in real life. I like to use the concept of time so that students can actually grasp how big these values are. Mega is 10 raised to 6, right? So it's a million. It's a million. How many days, weeks, or months do you guess is 1 million seconds? 1 million seconds. Just a wild guess. About a week, year, what, 40, what? 45 days. It's all good guesses, but it's about 11.7 something days. How much is 1 billion seconds? Absolutely. It's 31 point something years. Instead of seconds, now put dollars in there. That's the difference between a millionaire and a billionaire. Couldn't even dream of being millionaire. So that's the difference between a millionaire and a billionaire. 11 days versus 31 years. 31 years. If you had $1 billion and you spend like one every second, it would still take you 31 years to go through everything. Okay. Excuse me. Okay. There was a movie that came out a few years ago, In Time. Anyone see that? Anyone heard of it? Justin Timberlake. I like the movie very much. I know when you hear the word Justin Timberlake, it doesn't inspire much confidence about the movie. Still, it's not bad. The concept is in the movie is that every person on the planet had a clock built into their arm. And the clock signified their life. Okay, so they would grow from birth until they were 25 years of age. At 25 years, the clock started ticking. You only had a few days to live. So poor people, I mean, everybody had to work to earn not money, but time. The more you worked, the more time you earned. And basically, the costs keep going up. So you would work like 8 hours a day, you would only get paid certain hours. So if you didn't work enough, your clock stopped and you died. And that's what the movie is. So the concept is very interesting. The execution is also not bad, but again, it's not to everybody's taste. But if you have the time on a Saturday night, I know you're all busy students, you have always something going on, check out that movie sometime. All right, let's see, what else was there? We'll just stop here for today and pick up here again on Friday. Thank you very much, and I will see you on Friday.